I am happy to share with you some recent results we have with some colleagues right and here. Most of the results I will present are published in a paper in LAAS-CNRS last year. And the topic of the talk concerned the fact to modify the dynamic output feedback in order to take care of the presence of noise on the output. So the outline of the presentation is relatively classical. I will try to motivate the studies, and I will define the kind of controllers we will study during the talk. And I will present some results regarding the saturation redesign, and next dead zone redesign, to maybe, if I have time, to mention some applications of these techniques. And of course, I will conclude by some concluding remarks and perspective of the work. So for in a control, it is classical to take care with the presence of a disturbance in the systems, and in particular, in order to reject or to attenuate the disturbance in feedback design. In general, disturbance comes from external signal affecting the dynamics or the measurement noise, or the measurement, sorry. Several techniques can be used in order to deal with this problematic, in particular in the context of linear systems. The classical robust control theory like H infinity, H2 design, or LQG approaches. There exist also the approaches due to geometric approaches or the internal model regulators techniques. When we want to design a control using only the measurement of the system, we want to build some output control law. We can use the classical observer plus state feedback, but we can also build directly output feedback controller, for example, as mentioned in the reference of Scherer. It is very important to note that even if I am able to build a robust observer from a side, in another side, a robust state feedback, the fact to combine both does not lead to a robust output feedback. So you need really to study the robustness of output feedback control law. Of course, we know that in the context of linear systems and linear controllers, we have some limitation of the performance we can obtain. And in order to overcome such limitation, we can use nonlinear or hybrid techniques. And for example, I put several papers here dealing with the fact to add some, for example, hybrid techniques, like in the paper of Prier and Thiel, or Fiquera and all, or some papers from Algovers and so on. In the talk, we will follow a different route. We want to be able to handle the problem due to the presence of noise in the measurement of output measurement of the system, in order to reduce the sensitivity to this noise for the system. Of course, we know that in order to improve the sensitivity to measurement noise, we can develop ad hoc method, and we need to study the way to design an observer or a controller for different specific classes of systems. The solution we propose is to consider that we have in hand a certain observer or output regulator, and we want to propose a method to just modify this system in this controller in order to be less sensitive to high frequency noise. And we say that in a certain sense, we know this, and we want just to say how we can modify just a part of this in order to be robust for in presence of disturbance or noises. So in the talk, we will consider two kinds of disturbance. The first one is the outliers. That is, we can imagine that we have some strange output measurement, or we have some sporadic impulse noise affecting the measurement, or we can also consider persistent small noises. And we will present two techniques. The first one consists to modify the controller by adding some dynamic saturation, and we call this the dynamic saturation redesign. And we take inspiration from the first seminar work by Alessandri and Zakarian dealing with this in the context of observer. And we will also propose dynamic dead zone redesign by taking inspiration of the paper we did with my former student Cocchetti in the context of observer. Okay, so we consider the following system, classical. We are in the framework of linear systems. We will comment after in the conclusion what we can do for nonlinear systems. So we consider that we have this plant where XP is classically the state. We know the input because it's the output of the controller. We have the measure output way described like this, and way is a disturbance. Now we consider an output dynamical controller like defined like this in this block, where Z is the state of the controller, UC is the input of the controller, and defined in particular from the output of the plant. Okay, and for this closed loop, we suppose it's classical that the linear closed loop described by this block is globally exponentially stable to the origin, of course, when W is equal to 0. So we can recover also what happens in the context of observer. That is, for this, we choose A as the estimate state X hat P. We change the input of the controller, like the difference between the measure output way of the plant and the estimate output way at. We define F, G, H, and N like this, and from this definition, we will recover the classical observer with U is the state feedback using the estimate of the state. Okay, so of course, the first assumption regarding the fact that the open loop, the closed loop without disturbance is stable is a classical result and is necessary, of course, in order to be able to develop the redesign we will propose after. And of course, we know that we need to have some stabilizability and detectability of this triple AP, BP, CP. Okay, so the idea is now we have in hand a controller defined like this, okay, and we want, in fact, to modify the input of the controller in order to be robust, to become robust in presence of noise in the way of the plant. And we propose two techniques, and instead to consider that the input of my controller is directly way, we will consider that we have the input of our controller is a nonlinear function defined from a saturation or a dead zone. And saturation corresponds to the stud-born redesign or the dead zone redesign. That is a saturation like this or a dead zone like this. Okay. Here we suppose we denote square root of sigma V. V is a constant vector and sigma is a positive real. And sigma denotes the level of saturation or the level of the dead zone here. So what is the objective we want to do? And of course, the design we want to do is we want to design this scalar sigma. We want to choose sigma. So, of course, we want to preserve the global exponential stability when we have no disturbances W, And in presence of W, we want to ensure that we have a sort of input to state stability from W to X, or from W to the Y. Okay, so we want to be able to find a positive scalar M, alpha, and gamma satisfying this one, where we modify a bit the norm of the vector, because now I am adding, we will see more specifically after, I am adding a new state, sigma, and the norm of this new augmented state, X and sigma, has to be let down to this expression, and we will retrieve the classical ESS conditions. So first, consider the saturation redesign of the loop. So we consider that we have the control like this, we had this saturation in the input of the control, and now we consider that we have this adaptive law for sigma. So we add a saturation, but this saturation is dynamics due to the dynamics of the level of the saturation sigma. We choose this law by considering that lambda will be a strictly positive scalar to be designed, and R will be a symmetric positive definite matrix. And from this law, it is clear that if we choose an initial positive condition, sigma of 0, due to this law, sigma will continue to be positive. Okay, so with respect to this law, the positive orthant is invariant, or for one invariant for sigma. Okay, and the saturation is the classical one defined like this, as previously demonstrated. Okay, so now we are in hand this kind of closed loop, and we want to design lambda and R in order to ensure to improve the performance in terms of ESS in particular. So we can just rewrite the closed loop system in a more compact form. We consider that the dead zone is defined like this. That is, the dead zone of Y is the argument of the dead zone Y minus the saturation of Y. Okay. And of course, I can replace saturation from this expression, and I obtain this expression for the closed loop system, where the matrix A, B, B, W, C, and D are defined like this. Okay, so I suppose in all the talk that all the matrix of the control law, that is H, G, N, and F, are given. It is important also to remark, to observe that due to the first assumption I proposed, that is assumption 1, matrix A, that is this matrix, is a Ritz. It's normal. I have designed my controller in order to obtain this property. Okay, so it is important to note that I define sigma, which is a positive scalar. Sigma dot imply that sigma will remain positive, because this term is always positive or null. Okay, so it's the remark I proposed before. Just recall that what are outliers? We suppose that we can have some sporadic large amplitude disturbance affecting the output wave. And what happens in this context with the previous modification of the control law I proposed? If wave is constant, then sigma, that is the level of the saturation, tends to be a constant also. If an outlier occurs, then wave can become large, but the effect of the saturation is that the effect on wave of the saturation will be to obtain a small value for this square root, and in this case, mitigating the bad effect on the closed loop. If wave is growing because affected by an outlier, then sigma is increasing by the definition. Remember, sigma dot is depending on the wave transpose R wave. Then sigma increase, and in this case, we have a very large level of saturation. That is, it's like we have no saturation. And we denote this that we generate desaturation of the loop. Okay, so we have the following result now, considering the previous closed loop system I defined. Assume that there exists a scalar lambda positive, a symmetric positive definite matrix P, a symmetric positive semi-definite matrix R, and two diagonal positive definite matrices UG and UL, and a matrix weight not with no particular sign, such that the following inequalities holds. We will discuss the inequalities after, where H denote the Hermitian matrix. Then, if we are able to find P, lambda, R, UG, and UL satisfying these three conditions, then we can ensure that the closed loop where we define V, the vector V, for which all the components of V are the inverse of UL. Remember, UL is a diagonal matrix, so I take all diagonal elements and to build V, is finite gain exponentially ESS from W to X, that is satisfy this, and I can prove that there exists M alpha gamma satisfying this for any T positive. So just some ingredients of the proof. In order to prove these results, we consider the following Lyapunov function described like this, where we will try a quadratic part in X transpose PX and a linear part involving sigma plus this term, because we are trying to split the discussion between inside a certain ellipsoid and outside this ellipsoid. So when we consider this Lyapunov function, we need to design P, zeta, and mu here. We can, by studying this function, prove that we have this sandwich condition classically, where alpha 1 and alpha 2 are defined like this. We can, of course, observe, and it is a particular fact to this approach when we use saturation, dynamic saturation to modify the controller, we can observe that this function is not continuously differentiable in the set of measure 0, that is when X transpose Px minus lambda sigma is equal to 0. But we can observe that it is continuous and locally Lipschitz. Then we can use all the machinery for this kind of function. For example, you can have a look on these two papers. And in fact, we are trying to prove that we have this Lyapunov function satisfying the classical V dot negative and so on, almost everywhere. So we split the analysis in two cases. The first one is when I am inside a certain ellipsoid set described like this, that is X transpose Px strictly less than lambda sigma. And the second case, I am outside this set. Okay, so just we have a look on the first case, that is this one. So in this context, remember the Lyapunov function is this one. Okay, so in this context, this part is equal to 0. And I obtain the Lyapunov function described like this. If I compute the time derivative of the Lyapunov function along the expression of my closed loop system, I will obtain this one. Remember, I have a Lyapunov a saturation in the loop, so I need to use some condition in order to some mathematical abstraction to under the saturation. And in this context, we will use the regional sector condition. That is, we can prove that the dead zone satisfy this condition for any diagonal positive matrix UL and for any matrix Q and X, such that the dead zone of QX is equal to 0. That is for the set QX between sigma and minus sigma. So if we consider the augmented state Xi described like this with X and the dead zone, and we use the change of variable like this for a way. We choose zeta equal to a certain epsilon. We can, by using Young inequality and working a bit with fastidious calculation about this expression in order to obtain a hyperbond, we can hyperbond the v dot by this expression, okay, where we can define k bar L by this expression, okay. We have this in hand, and we have the first case. Now we can consider the second case. We can do exactly the same, but now we have this expression. So now the maximum between x transpose px minus lambda sigma n0 is this expression. So we have this expression for w. We can compute the time derivative of this function like this. And now, because we are outside the ellipsoid, really speaking, the ellipsoid described like this, that is the inverse, but we are outside. We will use global sector condition, and we can check that the dead zone satisfy this expression for the global condition, where G is a diagonal positive matrix. By defining exactly the same augmented state psi, like this, we will obtain the following bound for V dot by denoting K bar G like this. And Mg is a negative definite, but Mg is defined here. Okay. So now, by studying both case 1 and case 2, we can in fact observe that we have V dot always satisfying this, because remember, now I have a new dynamics due to sigma, so I am interested by bounding the norm of the new state x sigma, and I can prove that this V dot will be always less than this expression, which is the definition of ESS. Okay, so we can, of course, remember we have 3 conditions. Here we have the condition with the global condition. Here we have the condition with the local condition. Here we have the relation for the local sector condition associated to this expression. But we have 3 matrix inequalities to solve. And the first question we can have is it always possible to solve these conditions? And the answer is yes. We can prove that we have the feasibility of these conditions. So we can prove that thanks to the assumption 1, there always exists parameter P, R, UL, UG, way, big way, and lambda satisfying the condition of theorem 1. Okay. Okay, now we have a condition with 3 matrix inequalities. We have results proving that we have the feasibility of this condition. But we can, if we observe the condition, what we can observe is we have the multiplication between lambda and R, lambda and P. Okay, and also this lambda here, but we can replace place lambda in other place. So what happens with this? We can observe that we have the product between lambda and other decision variable. So we have a quasi-convex conditions. But in the context of the condition, if we study the conditions, we can see that we have to solve a generalized eigenvalue problem in the scalar parameter lambda. So we know that in MATLAB, we can find some routines in order to solve this problem. Okay, so it is clear, if we have a look on the condition, that if we fix lambda, the conditions are completely homogeneous in the decision variable P, R, UL, UG, and Y. And so if we consider this condition, or we multiply all the decision variable by scalar C, we will obtain exactly the same feasibility for C positive, of course. So we can imagine to use the following design procedure in a certain sense. We fix lambda small enough in order to ensure the feasibility of the LMIs. We impose P strictly greater than the identity matrix. And it is possible due to the homogeneity of the conditions in the decision variable. And we try to minimize the trace of error. And doing this, we will obtain a certain fast reduction of the parameter sigma, with the objective to eliminate measurement outliers. We can consider the following example. We consider the following nonlinear systems due to this paper, representing the longitudinal dynamics of an aircraft flying at high speed, with a description of what is V, the speed, and so on. We can remark in this system that the signals E and Q are the control input, and gamma and theta are the outputs. W1 is a wind perturbation. So for the moment, we do not use this. And the noises measurements are W2 and W3. Okay. We can linearize this system around the following equilibrium point. V0 is given, in order to obtain the following matrix AP, BP, described like this. And we can recover the previous plant in order to apply our technique. For this, we choose G, V0, and L at this value. And we consider a pole placement in order to obtain the closed loop pole at this, having the real part in this set. So we simulate the system. Here we have the behavior of the disturbances. Here we have the behavior of the norm of the vector x. And we can see that in blue, with the redesign, saturation redesign, we have a better behavior. And if we look at what happens for the norm, we have a decrease of the norm thanks to the saturation redesign. So we can conclude that by using a dynamic saturation, we attenuate the effect of the outliers. But if we have false noises affecting the system, we are not able to reduce this at steady state. It's a reason for which now we use another technique using dead zone, dynamic dead zone. So we consider this, that is now, instead of a saturation, I use a dead zone directly at the input of the controller, with the same kind of adaptative law described like this. Remember, lambda is positive and R is a symmetric positive semi-definite matrix. Okay. And the idea is it possible to cut the effect of the noise on the output? So I can use the same machinery as previously. Remember that I have always this relationship between the dead zone and the saturation, and I can write the closed loop like this with exactly the same matrix as previously. And as previously, the matrix A is Hurwitz. Matrix A described here. So now I can obtain the following second result, like this. If I am able to find a positive scalar lambda, a positive definite matrix P, a positive semi-definite matrix R, and a diagonal positive definite matrix UG, satisfying this inequality, then, where this notation is always the Hermitian matrix, then I can conclude that the closed loop with V is the inverse of the diagonal element of UG. Previously, it was the inverse of the element of UL. And the closed loop with this vector V is finite gain exponentially ESS from W to X, that is satisfied these conditions. So some ingredients of the proof. In this context, we choose a simpler Lyapunov function described like this. So we retrieve that we have a quadratic part and a linear part in sigma, quadratic part in x. If we study the sandwich condition for this Lyapunov function, we can obtain the classical one where alpha 1 like this, quite similar to the previous one, except the definition of alpha 1 and alpha 2, of course. And in this case, we do not need to split the analysis into cases because we have just one case. And it is a reason for which we have just one set of inequalities. So we compute the time derivative of this Lyapunov function. And now we have a dead zone, but dead zone is related to the saturation, of course. So we will use two kinds of expression. We will use a sector condition on the saturation like this, a global sector condition like this, but now it is written on the saturation. And we will also use this condition is just using the fact that saturation is always less than sigma, between sigma and minus sigma by definition. Okay, so we can work on this. We had, as previously, we had the condition on the saturation by using the S procedure on V dot, and we can obtain the following bound for V dot like this, which is equal to this expression, where epsilon is a positive scalar. And we use also some tricks in order to obtain these expressions. So if we work on this expression, again, by defining psi like this extended vector, and using the previous bound here, we can obtain the following bound for V dot, like this, where kappa bar G is defined like this. And G is defined from this expression, okay? And by definition of the theorem is negative definite. So by working again on this expression, we can recover an expression similar to this one, where we can redefine epsilon bar and kappa bar from this expression, and we can therefore conclude that we have the ESS property. Sorry. So we have exactly the same problem as previously. Is it possible to prove that these conditions is always feasible? And of course, the answer is yes. And as previously, we can prove that under assumption 1, there always exist parameters P, R, UG, and lambda satisfying the condition of theorem 2. Okay, and we can observe as previously that we have lambda multiplying UG, so we have quasi-convex condition in the decision variable. Sorry. So we can also propose a design procedure in order to design P, R, UG, and lambda. We fix lambda. We impose now P less than the identity. And we have also the homogeneity of the condition in P, R, and UG. And we maximize the trace of R. We can also add something by trying to maximize in a certain direction corresponding to the sensor most affected by the persistent noise. And we can prove that we improve the sensitivity, the performance in presence of noise. And if we consider the same example as previously, we have always the behavior of the noise, and now we have in red, as previously, the evolution of the norm of X with the standard regulator without the dead zone, and in blue, the regulator with the dead zone. So we improve, not always, but in general, we improve the behavior of the norm, and we can have exactly the same look as previously if we compute the norm on this in this interval of time. We have a less value for this technique using the dead zone variable dynamics. So we can conclude that the dead zone adaptation allow to attenuate the effect of small noise at the steady state, but in this context, we cannot consider outliers, that is here. Okay, we have applied these techniques in two contexts. In the context of the estimation of lateral speed for a vehicle. In this context, we can represent, published in the paper in here, defined here. We can represent the plant through an LPV model, where R is a yaw rate, and the model is described like this, where AR is described like this and C here. We can compute, design, air-dependent kinematic observer. That is, we use the classical LPV framework, and we will obtain the following observer again like this, that is depending on the parameter. And if we substitute this classical entry of the observer by the dead zone, we reduce drastically the sensitivity to the noise, like we can see on this picture, where in orange we have the diminution of the noise with respect to the brown case. And it is interesting to note that we use also this in the context of control of anesthesia, that is the control of the depth of anesthesia. In this context, we have a different system. We have a compartment model described like this, representing what happens with when the drug is injected in the body of the patient. So we have the drug involving the muscle, the fat, the blood, and the brain in a certain sense. Of course, there is several signals measured by the doctor, the anesthetist, in particular the EEG signal. And in general, these kind of signals are very corrupted by noises. And in some case we study, we have 10% of noise on this signal. The other important fact when we consider this kind of system, we can observe that we have slow and fast dynamics, because muscle and fat are not so interesting to study what happens in the body of the patient, but we are focusing on the effect on the blood and on the seat effect that is in the brain. Okay, so we can separate a fast and slow part. Slow are muscle and fat, and fast are blood and brain in a certain sense. And differently from the classical singularly perturbed system, we are interested by controlling the fast part and not the slow part. Okay, so we focus on the control of the blood and effect seat. So we can represent the system we study, because we compute an observer, we compute K1 and K2 in order to stabilize the system, the flow, the fast dynamics, to attain the good reference for the system. And we consider a dead zone affecting the new controller. And thanks to this, we really drastically reduce the noise for the system. And here in red, we have what happens for the system without this dynamics dead zone. And in blue, it is a similar, the same signal, but thanks to the dead zone, we really reduce the noise. Okay, so now I am able to conclude my talk. We have presented some adaptive nonlinearities techniques such that saturation and dead zone adaptation in order to improve the performance of output feedback controllers in presence of measurement and noise. We can do the same with observers. The method we propose is relatively flexible, because here I presented the brick, but we can modify a bit. It was typically the case for the problem of anesthesia. And the objective, by redesigning the observer or the output feedback, was to preserve the ESS and also to improve the performance. In the linear case, the conditions are quasi-LMIs and very simple to use, and we can prove that we have the feasibility. Of course, this kind of work opens the door for several perspectives. For example, we have studied the nonlinear case in the context of observation, but not in the context of output feedback regulation. So maybe we can expand the result I propose in the context of nonlinear continuous time system. I presented a condition in the context of continuous time system. It could be interesting to use also, to study also the discrete time systems. And I presented the case where we use saturation and dead zone with the famous law sigma dot equal to blah, blah, blah. But we are thinking that maybe we could, of course, combine both nonlinearities, but maybe we could use different nonlinearities. For example, we are discussing about the fact what happens if we use nonlinearities like a backlash, that is nonlinearity with some memory effect. It is interesting or not. For the moment, it is an open direction on which we are working with my colleagues. And here there is several references dealing with this problem. Thanks a lot for your attention.